In the last lesson, with some information I gave you and kind of finding patterns, you were able to write a Maclaurin polynomial for the sine of x. Well, in this video, I'm going to show you how to use some things we know, so we're going to get a little bit creative, to use some things we know already in order to write Maclaurin polynomials for other functions other than sine x. So the first one we're going to look at is, we're going to try writing a Maclaurin polynomial for the cosine of x. Well, you could guess and check. I could give you some information, but let's be a little bit more creative than that and try to work not so hard. So you figured out, or we figured out in the last class, that we have a generic equation for the sine of x. So generic Maclaurin polynomial for sine x is x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on in that pattern, until we get to the general term, which is -1 to the n, x to the 2n plus 1 because we have odd exponents, and then 2n plus 1 factorial, and so on. So we know that is the Maclaurin polynomial for the sine of x. And we're trying to write a Maclaurin polynomial for the cosine of x. So let's think creatively for a moment. How can we use this sine function, this sine polynomial, to write a Maclaurin polynomial for cosine? I hope you're thinking about it. I'm not going to pause or anything. Let's think about some calculus here. We know that the derivative of sine x is equal to the cosine of x. So if we find the derivative of this Maclaurin polynomial for sine, we'll have a Maclaurin polynomial for cosine. Okay, so let's give that a try. Cosine x equals the derivative of this polynomial. I'm going to give you a moment to try it. See if you can simplify this, because it's actually going to be important to simplify this. I know we've been trying to cut corners and not simplify everything, but in this case it's going to be important to simplify your answer because there's a pattern to this. Okay, I'm going to pause here. I'm going to let you try it. All right, welcome back. I'm going to find the derivative of each one of these terms. So we've got cosine x. The derivative of x, that one's nice and straightforward, that's 1. For the next one, I'm going to bring the 3 out in front, because really this is like saying 1 over 3 factorial times x cubed. Not that one, but the original, not the derivative. So this is 1 over 3 factorial times x cubed. So we're just going to use the power rule. I'm going to bring the 3 out in front. So really this becomes 3x squared over 3 factorial. We'll simplify in a minute. And on the next one, I'm going to bring the 5 out in front. 5x to the 4th over 5 factorial. I should have left way more space. Dot, dot, dot. We're going to do the same thing here. That's the same pattern. We're just going to bring this 2n plus 1 out in front and then subtract 1 from it. So I am going to take up more space on this one. So we've got 2n plus 1 and then -1 to the n. And then subtract 1 from that exponent, so this is x to the 2n, all over 2n plus 1 factorial. All right, let's do some simplifying here a little bit. 3 factorial, I know, is 3 times 2 times 1. So 3 factorial is 3 times 2 times 1, and I know that 5 factorial is 5 times 4 times 3 times 2 times 1. So when I try to start simplifying this a little bit, I notice that the 3's will cancel, the 5's will cancel, so what I've got left on this first one is 2 factorial. So I can start writing this out a little bit better now. I've got 1 minus x squared, and 2 times 1 is 2 factorial. And then I've got x to the 4th, 4 times 3 times 2 times 1 is 4 factorial. So if I continue on to my general term, I can see that the 2n plus 1 will, let me back up. 2n plus 1 factorial, let me write it this way, is 2n plus 1 times 1 less than that, so times 2n, times 1 less than that. So now I can see that these 2n plus 1s are going to cancel each other out. So here's what I'm left with. You might have seen this pattern already. This is 2n factorial. So just like that, we have written the Maclaurin polynomial for cosine by using the Maclaurin polynomial for sine. So these two polynomials are something you must know. You must be able to recognize that cosine has even exponents, that cosine of x starts with 1. You must recognize that sine starts with x and has odd exponents. You must be able to rewrite this at the drop of a hat. Just like you know that sine squared plus cosine squared equals 1. You need to know the Maclaurin polynomial for sine and the Maclaurin polynomial for cosine. Just like that. You have to know that quickly because it's going to come in handy. Okay, so let's do another example. I'm going to use a different color other than purple. Let's do another example. I'm going to ask you to find now the 8th degree Maclaurin polynomial for the cosine of x squared. 8th degree. So when we get to the exponent that has the 8th power, we'll stop. Well, cosine of x squared, let's think about how we can do that. We just found in the last problem, cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And if I kept going, this would be x to the 6th over 6 factorial. And I'm not going to go on ... because this is only asking for an 8th degree polynomial. So I'm just going to stop here. This is good enough to give me what I need. So this is for cosine x, but the problem's asking for cosine of x squared. So that means in the function, instead of having x in the function, we'll have x squared in the function. So the cosine of x squared can be found by replacing each of these x values with x squared. So it'd be x squared squared, x squared to the 4th, x squared to the 6th. And if I simplify this, x squared squared, that's x to the 4th over 2 factorial. X squared to the 4th is x to the 8th. So there's my 8th degree that I'm looking for. That means I don't need to keep going. I don't need that last term. That last term is extra. So here's the answer to that question. Here's my 8th degree polynomial for the cosine of x squared. So I'm using old polynomials. I'm using things I already know to write polynomials for new functions. And these polynomials, remember, these polynomials are fitting the curve. If you were to graph the cosine of x squared, and you were to graph 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial, it would be a decent fit for a while. It won't fit perfectly for all values of x, but it'll be a pretty good fit for a while. Okay, let's try another one. We've seen this limit before, the limit as x approaches 0 of sine x over x. And you may have memorized that this is 1. You might be picturing the graph that this is 1. But we're going to use Taylor polynomials to show that this is 1. Okay, so let's rewrite this. We've got the limit as x approaches 0. Actually, why don't you take a moment, because you should know this. Write down the polynomial for sine x without looking, if you can. Okay, let's try it. So the sine x function starts with x, because this is all odd exponents. So then it's x cubed over 3 factorial plus x to the 5th over 5 factorial. And we can keep going. Let's just stop here for now and see if that's enough. And then divided by x. if I plug 0 in now, I end up with 0 over 0, so that's not going to be helpful. But what I can do is simplify this expression. I can divide each one of those terms by x, because it's the sine of x being divided by x. So if I divide out an x from each one of those terms, this x divided by x is 1. This divided by x is now x squared over 3 factorial, and then this is x to the 4th over 5 factorial, and so on. And I could keep going forever and ever. But the point is, as x approaches 0, all of these become 0. 0 divided by 3 factorial is 0, 0 divided by 5 factorial is 0, and so on. The only thing I have left then is 1. So I can use Taylor polynomials to evaluate limits. I can use Taylor polynomials for a lot of things. And we'll talk about more of those things as time goes by. But in the meantime, actually I'm going to pause here and make a new video because this next idea is kind of big and I want it to have its own video. So I'll see you in the next one.